This program is brought to you by Stanford University. Please visit us at stanford.edu.
So let's take a little trip through memory lane. What was the first thing you learned in the class? Units, Perry's.
Burning cats.
Burning cats. Money. Speak to me, Godzilla. Flow sheets. Mass balances. Mass balances without reaction, mass balances with reaction, and recycle. And then after that we did what? Heat transport, energy balances. And you actually learned how to design a heat exchanger. So at least you get something useful. And then where'd we go after that? Scaling and dimensional or dimensionless analysis. Either way, one or the other. And so we're going to pick up on scaling. What'd you learn about scaling so far? What? Godzilla existed? What'd you say, Michelle? Not very good at it. You learned a technique to find dimensionless groups that govern physical occurrences. What was that called, that theorem? Buckingham Pi Theorem. So that's simply a way of thinking about gathering together all the parameters that you think are important in describing a problem and trying to reduce those parameters to the minimum number of dimensionless groups that can be used to describe that activity. And what that does is it helps you decide the kinds of experiments you're going to do, how you're going to vary parameters, and it reduces essentially the data sets that you are required in order to describe that system fully. And we'll give you opportunities to solve more Buckingham Pi problems so you can get a better sense of how that's used. Because actually by the time you take a few more Chem E classes, you'll find that we aren't going to be working problems with dimensions. We really try to put everything in a dimensionless form and then work it. And that's good for one reason, because when you get to the final answer, you don't have to check your units, because there aren't any. But you still have to check what? Yeah, does it make sense? Does it, does it make, and Perry's, that's right, check Perry's. So we're going to, you're going to be doing a problem in pharmacokinetics for your one of your homeworks. It's basically a project, it's a computer project. And so I'll give you an idea of what it's going to be. Basically what we're going to do is based on your body weight, so everybody is going to work a different problem unless you all say you weigh the same, which of course I won't buy into because I can just tell by looking that that's not true. Based on your body weight, we're going to build a virtual human in the class. And that virtual human we're going to program into a computer so it responds like a human would. And we're going to then have you become a virtual human in the homework and take a massive drug overdose. And you are going to have to save yourself. And you get to do that in your homework. And you have to then, the answer to that is the strategy you used to save yourself. And there will be computer printouts that verify whether you did or not, so you just can't say, I saved myself, and turn that in as the answer. You'll have to show actually the strategy you used. And the way you save yourself is that there is a machine sitting next to you called a dialysis machine, an artificial kidney, which you can virtually turn on. And what that does is it dialyzes the blood in you, the virtual human, to get rid of this bad drug. But we're not going to make it so simple that you just sit down and plug the dialysis machine in and wait. There could be power failures. There could be people who tell you there's certain times of the day you can't use the machine, kind of real world things like that. Someone comes in and tips the machine over. and still connected to you. Oh yeah, we'll give you all the constraints. And in order to build this sort of virtual human, we need to have some understanding of the scaling laws and rules that relate sort of how you're going to scale yourself to this problem. Now, there's another activity where scaling is really important, and that is in the development of new drugs. Now, if a pharmaceutical company develops a new drug, do you think they go out and they get, to the shopping mall and get 20 volunteers, stick them with the drug, and then sort of sit and look, see what happens? They use mice, or they use rats, or they use sometimes students, but they use typically small animals. And so what's the scaling problem there? Mice are what? Fat. They're different proportions. Yeah, they're different proportions. First of all, they're smaller. They clearly have some different metabolic rates. Have you ever seen a mouse, run around the room? I mean, it looks like it moves faster than you do when you move around the room versus an elephant. And so if you're sticking the drug into the mouse may metabolize and eliminate and use that drug differently than you would, but you have to connect what happens in the mouse to a human, or what happened in the rat to a human, or in the monkey, or in a dog, or in a cat. And to do that, you need to have scaling rules. So you know that whatever is happening in the mouse, you can then connect that to a human. So it's hugely important because it's used all the time. So that's what we're going to do today. We're going to sort of talk about the scaling rules that allow you to go across species in terms of the behavior of drugs, and then we'll finally get into your problem set. So here are some scaling rules, and I'll show you where they come from. So the scaling rules that we're going to come up with today are that the body surface area of an animal, this could be a human, it actually turns out it applies to a tree, is proportional to body weight to the 2/3 power. We're going to see that organ volume in animals is proportional to the body weight. That is, your organ volume is proportional to body weight. Your skeletal mass is proportional to your body weight to the 1.13 power. And your metabolic rate is proportional to body weight to the 3/4 power. And you might say, where on earth do those things come from? How do I know that? Well, I go do some experiments. And here's the results of these experiments. So let's look at this top one first. So this is a plot of body surface in square centimeters versus body weight, and that's in grams, by the way. I don't know what that symbol is, but it's body weight in grams. And this line, this green line I've drawn in, has a slope of 1. Just so you know that. Now, here's the data. The data you see goes from body weights of about, what is that? About a gram, up to a ton. This is a log-log plot. And you see that if I plot the body surface versus the body weight, the data all fall on a straight line with a slope of 2/3. So that body surface area is related to body weight by a 2/3 exponent. Remember on the previous page I had body surface area goes as body weight to the 2/3. So this is where it comes from. Now you have to ask yourself the question, does that make sense? Now if you apply this to a sphere of unit density, that's what this line is. A solid line represents a sphere of density 1. So this is how the surface area and the weight of that sphere are related. And that's 2/3. And where do you think that comes from? We talked about that last time. How does the area grow? As the square, and how's the volume grow? Is the cube. So you see the 2/3, how that comes in? But why do you think the data are all above this line and not below it, or not on it.
We're not spheres?
We're not spheres. And our density is, 1 gram per cubic centimeter is like water. We're not far from that, although you do know that if you jump into a pool, you can float for a while, and then you sink. And then after the gut organisms, which are still living after you die, start releasing gas, and you rise to the surface again, like a cork. That's what happens. But we're not a sphere. In other words, a sphere is an object that has the minimum surface area per volume ratio that you can have. That is a geometric object. So if you're not a sphere, if you're anything else, you actually have more surface area per volume. And that's why the curve is above it. But not much, but it certainly has the same slope. So it's interesting that this goes over.
How do you measure surface area
of
anything, of an animal?
I take you, and I take your skin off and lay it out, and take a planimeter and measure it. Now, you would probably object to having that done. Planimeter is an ancient engineering instrument that I used at Berkeley in the old days, which allows you to actually trace the perimeter of an object, and it actually calculates surface area mechanically. People don't use that anymore. They use computers to do that, but that's how we used to do it. It's a cool little instrument. And in fact, I was in a law case, you bring that up, once where I had to measure areas of ponds that were evaporating nasty materials. And I'll talk to you about it when we do the environmental stuff. And I got into the courtroom, and the attorney, who's a young guy, says, doctor, how did you do that? And I says, I used a planimeter. There's nobody uses planimeters, doctor. And I said, why not? It's in the Smithsonian. And I says, well, things in the Smithsonian used to work. The rockets, the airplanes, the cars. My planimeter works. I just happen to have one. Doctor, are you an expert on planimeters? And I said, well, I know how to use them. Yeah, there aren't any left. You're the only one on earth. And she goes to the judge, says, I want him out of here. I want him out of the courtroom. And the judge threw me out. And so I had to go find a guy with a computer who could take pictures of these things and have the computer determine the area. Came back, had it within less than 1%. Judge looks at me and he says, I'd like to see his planimeter. It must really work well. I mean, this is like the legal system at work. And so anyway, that's planimeter. That's what it does. It measures surface area. So there's one of our scaling laws. And the way you get it is you get it from data. Now, here's another one that we talked about. This is lung volume plotted versus body weight in kilograms, spanning, looks like about 6 orders of magnitude, from the bat to the whale. Now, this is just lung volume. The lung is what? What would you call the lung? An organ. It turns out if you do this for the heart or the liver, the brain, it all falls on a line whose slope is 1. So that organ volume goes as body weight to the 1 power. Now, you wouldn't have known that had you not done the experiments. It's kind of interesting, I think, that that's the way it is. Look at this, a bat, and a shrew, and a mouse, and a rat, and a guinea pig, armadillo, rabbit. Everyone know what a marmot is? Any of you hiked in the Sierra Nevada? They're kind of big, fuzzy, larger than squirrels, sort of the size of a beaver sometimes. A monkey, a cat, raccoon, dog, goat, pig, man, porpoise, bear, cow. Man, dugong. What is a dugong? Tell me. Tell me a dugong.
Isn't it like a seal kind of thing?
It's a manatee. You're right. It is but what's the difference between a manatee and a dugong if they're the same? The what?
Freshwater and saltwater.
Close. But that's good, Emerson, close. I mean, I may be wrong. I think the manatees species live in the Atlantic Ocean, generally in warm coastal waters, and I believe the dugongs live in the Pacific side. And I think only because of the Panama Canal that you have these intermediates that meet in the canal and mate and make magons. Yeah, these are ugly suckers. If you were born a manatee or a dugong, you would wish to hell you had been born something else. They have these big, nasty snouts, whiskers, and they have prop marks all up and down their back because they float right under the surface, and these guys in these cigar boats come along and just groove them out. And this has been it's a real problem if you're a manatee when that happens. I mean, it's like having a wearing blender move from your butt to your neck and take out, a lot of tissue. And it's too bad because they're very docile creatures. They just sort of float around. They're called sea pigs, is another thing that they call them. But nonetheless, they fall on this scaling law. So there's another scaling law, which I think is kind of interesting. Now here's another one. Again, this is data, experimentation. And this is plotted on the ordinate is metabolic rate in, I don't know what that is, kilocalories per hour, metabolic rate versus body weight. This is again in grams. And if you want to correct, unless I already did it, 10 to the 0 is 1 gram, 10 to the, that's a 3. This is a kilogram, and then up to a ton. Look at this. This plot spans 18 orders of magnitude of body weight. So who do you think these guys are down here at 10 to the minus 12 grams? These are like bacteria, microorganisms. And you come all the way up here and you get up to things that are weighing around a ton. So who do you think's plotted up here? Things like whales and big guys. Godzilla. So here's a slope of 1. Here's a slope of 2/3. And you can see that all this data falls on about a slope of 3/4. Now that's kind of interesting, but let's ask some other questions. So down here we have the unicellular organisms, so this would be bacteria, yeast, and so forth. And then you have these poikilotherms. What is that?
Multicellular organisms.
Anyone know what they are? Yeah, they're unable to control their body temperature, so they take on the temperature of their environment. And then you have the what is that, homotherms? I can't read it, whatever it is. Yeah, I think it's this is old language. This plot comes from the time of the Romans. And so these are what you call your warm-blooded animals, where they control their core temperature at a constant value independent of what the external temperature is within limits. Unless you're up on top of Mount Everest nude, you kind of run out of heat after a while. Then you get all stiff. But think about what this says about how it explains to you sort of the behavior of down here of a mouse versus the behavior of an elephant in terms of your experience in watching them. So as the body weight goes up, the metabolic rate is going up to the 0.75 power. If it had been to the 1 power, you'd go to the zoo and the elephant would be running around just like a rat. And there'd be no way to contain them. And so that's evolution has caused them, you see, to slow down so that we can have them in a zoo. So the larger the animal becomes, the more the metabolic rate declines as a function of body weight. So you should be happy as a clam that this slope isn't greater than 1. I mean, that would really be nasty. I mean, you know, elephants running around looking like rats on, you know, super Prozac or steroids or whatever. So anyway, that's an interesting thing, metabolic rate. Now, so these are scaling laws that we can use to help us in relating what happens in one species to another. So now I'm going to show you, this will make your head spin. This is actual data. So let me, before I put this up, of course you're already peeking at it. There is a drug called methotrexate. And methotrexate, does anyone know what methotrexate is used for?
Rheumatoid arthritis.
It is used for rheumatoid arthritis. It's used for psoriasis. But more often it's used as a chemotherapeutic agent. It tends to cause cells that are rapidly dividing. It attacks cells that are rapidly dividing more selectively than it attacks cells that are not. And since cancer cells are rapidly dividing, it tends to preferentially go after them. In psoriasis, where you have skin cells that are rapidly dividing, it tends to go after them. The other thing it does, though, is it goes after your liver. And so this is a problem. It's a bad side effect of this drug. But nonetheless, if you were asking the following, well, I would like to know what the pharmacokinetics of methotrexate is in man. Now this is, let's say we haven't done any experiments yet. And what I mean by the pharmacokinetics is, once I infuse the drug into man or a human, there'll be a plasma concentration in the blood that is achieved based on how much I dose in. And then if I wait, so you take a shot of this stuff, and then you measure the plasma concentration in time, and you can see it will drop time after injection. And you'll notice here's some data for man. Here's some more data for man. Here's some more data for man. Now what's the difference? The difference is this was an IV infusion of 10 milligrams per kilogram of body weight in a 70 kilogram man. So you put this much in, 10 milligrams per kilogram body weight. The plasma concentration starts up here in micrograms per ml, and it drops in time. Why do you think it's dropping in time? It's either being metabolized or
Fusing?
It's excreted.
What's that? Excreted. Okay, you got that one. All right. Now, here we see, take that one off the tape. Here we see IV of 0.1 milligram per kilogram, and it's down here. First of all, why is the curve down here relative to this one, do you think?
Smaller dose?
Smaller dose. All right. Now, we don't want to put this stuff in man. What we'd really like to do is put this stuff into an animal and predict what would happen in man. Because we don't want to run those experiments in man to start with. And so you can see we could have picked a rat. Here's a rat, those curves. Or there's mice. There's a mouse there. I think there's some other mice in there. You can look at there. Here's a monkey. Here's another mouse. So first of all, when I look at all the various mice, what do you think is the difference in those curves? The dose. And you notice that the slopes of these curves are quite different in man than they are in the mouse and in the monkey and in the rat. Now why is that? Different metabolic rate, metabolic rate of taking up the drug or excreting the drug. So they all behave a little bit differently. But what you'd like to do is be able to do these experiments, say in a mouse or a rat, and be able to predict what would happen to a man. And that's where scaling comes in. Is there a way and this would be a tough problem if I were to, suggest this to you, find a way to take and plot the same data such that it all falls on one line. Because if it all fell on one line, say for a rat or a mouse or a dog or a man, you could use that one plot to construct it with animal data, and yet you could pull human predictive data off of it. And that's what scaling gets you. So I want to show you the power of scaling because I think it's pretty dramatic. And by the way, this in fact was used. I mean, this is actually from a publication back in the 70s. Bob Dedrick, Ken Bischoff, friends of mine. Dedrick worked at the NIH. Bischoff was a chemical engineer at the time at Cornell. And they came up with these scaling arguments. This is about the time these kinds of scaling arguments entered into the, shall we call it, into the profession. So let's ask ourselves, how may we scale or plot this ordinate differently? Now, if you look at the ordinate, you can make the assumption, it may be proven wrong, but one thing is looking at this data as you reduce the dose, is that the plasma concentration that initially emerges after a dose could be normalized to the dose per body weight. In other words, we can see that as the dose declines, the position of these curves decline. So there must be some relationship between the plasma concentration and the dose per body weight. The higher the dose per body weight, the higher the concentration. The lower the dose per body weight, the lower the concentration. If those were linearly related, I could just divide one by the other and take that away. Do you see that? Sorry, I didn't mean to put the laser in your eye like that. Are you okay? It did wake you up, I noticed. That's good. Your eye's bleeding, but that's okay. It's called LASIK. You just had LASIK surgery. So one thing is you might just plot the ordinate as plasma concentration of dose per body weight. Now, it could be nonlinear. It's possible that the relationship of the plasma concentration to the dose per body weight could be related in some nonlinear way. But if you stop to think about it, maybe not. I mean, you're just infusing a certain amount into, think of it like a tank. And if I double the amount I put into the tank, you'd expect the concentration to double. I mean, the amount of fluid it's going into is staying relatively constant. And since it's dose per body weight, I've taken out of the fact that our tank sizes are different, because I've already normalized that. Now, how about the abscissa? Now, this is tougher. Time after injection. You might expect that in a mouse, you see in the mouse how it's dropping a lot faster than it does in man? That might have something to do with how the drug is processed in the body. And we have to ask ourselves, is there a way, are there some scaling laws at work here that would help us understand that? So first of all, the drug is certainly used by the cells, but it is a drug that gets metabolized very rapidly in the kidney, meaning you excrete it. Same thing happens with vitamin C. I don't know if you remember Linus Pauling said take massive doses of vitamin C and you won't get the common cold. And he was right. You do need massive doses of vitamin C because the more you take, you just pee it out really fast. It's like drinking a 6-pack of Bud. Same sort of thing. But some of the vitamin C will be taken up in your cells, but most of it goes out. And so really to try to understand what's happening to methotrexate is you make the assumption that really you take it in, and the reason the concentration is dropping primarily is because it's being taken up, metabolized by the kidney. Well, then how do we relate that notion, the stuff that's going to the kidneys? If it goes to the kidney, what has to happen? If I put the drug in my arm, it gets into the bloodstream, and where does the blood have to find? It's got to go up here, it's got to go through the heart, it's got to go out my aorta, it's got to go down to the 2 renal arteries, and it has to go to the kidneys. So the rate at which this happens must have something to do with what in your body? How fast the blood is circulating in your body, or what's called the blood transit time. So what is the blood transit time? Well, it's the volume of blood you have, think of it like a tank, divided by the volumetric flow rate. So what's the units of this? Volume divided by gallons per hour. It's time, isn't it? It's the residence time on average. And you say, okay, well, the blood transit time is probably different in a rat than it is in an elephant, than it is in a man. So this is one thing we have to consider. Well, blood volume is proportional to body weight because it acts like an organ. You know, whether it's, you know what the largest organ in your body is? Your skin. All right. So what about the volumetric flow rate? So we know that blood volume is proportional to body weight. What about the volumetric flow rate, the denominator? Well, that volumetric flow rate is going to be proportional to the cardiac output, how fast your heart is pumping blood. Well, what is the cardiac output related to? Well, the cardiac output is probably related to your what? Your metabolism, right? And we know here's our metabolic rate is related to body weight to the 0.75 power. So all this would say is that the flow rate to the kidney, the volumetric flow rate to the kidney, is proportional to the cardiac output, which is proportional to the metabolic rate, which is proportional to body weight to the 3/4. So I now know that this flow rate is proportional to body weight to the 3/4. I know that blood volume is proportional to body weight. And so the transit time must be proportional to body weight divided by body weight to the 3/4, or body weight to the 1/4 power. Now that's not something that's real obvious, is it? I wouldn't have been able to guess that. And so what this is suggesting is that on the ordinate we plot plasma concentration normalized to dose per body weight. We talked about that. And on the abscissa, we plot the time since injection normalized to body weight to the 1/4 power. And if you take all the data on that previous slide for all those animals and plot it in this way, all the data fall on a single line. Now that's pretty powerful, because what it says is the following. I can get this line by doing experiments in a rat or a mouse. And then I can ask the question, if I dose you, if I know your body weight and I know the dose, I can find a spot on this curve, a value, say 0.2, and I can come over to here and I can come down and I can tell you the time after injection that the concentration in your body will be 0.2. If I come out here, I can tell you the time after which a concentration will be 0.04. Because this works for man as well as any of the animals. So here, in fact, without having to do the experiments, I can describe in a predictive way the fate of this drug in the body. And this is how drug discovery is done. Yeah? Yeah, this has been proven. Yeah, remember there were the data with man? So actually mixed on this curve are the human data. But you wouldn't necessarily know that if you didn't do it in humans, right? So the reason that you want to know this is because what this allows you to do is generally the data have shown that you need to have, let's say, for methotrexate to be effective, you need to have a value of 0.08, let's say, in these units after a certain period of time. And so you'd want to know in man how long that would be. I mean, you can do it in animals, but then you could predict how long that will be in man. Remember, this time thing is not in seconds. This is in seconds per body weight to the 1/4. It's got some strange units. If I wanted to find out what the actual time was, what would I multiply the numbers on the abscissa by to get real time? Body weight to the 1/4 power. Right, exactly. So this is really a very powerful outcome using these very simple. So let's see. I think I worked out an example here. Let's see if we can do it. And I'll use your help, and you can read off the diagram, okay? This was complicated because I had to do something to the 1/4 power, and I wasn't quite sure how to do that on my calculator. I couldn't find a 1/4. So here's the question. We want to know what the plasma level of methotrexate is in a person weighing 160 pounds who was given 1 milligram per kilogram of drug. So, and we want to know what it was in 8 hours, after 8 hours of injection, okay? So here's the question. I give somebody 1 milligram per kilogram of drug. The person weighs 160 pounds, and I want to know what the concentration in the plasma will be after 8 hours of injection. So tell me how to work this problem.
First, fix the units.
What's that? Go ahead.
Fix the units first.
Okay. So what do you want to do?
Kilograms.
Okay. We can do pounds to kilograms. What are we going to? Let's just do that in terms of the whole calculation if you want, or we can just do it now if you want.
So
Help me. What's that? Okay, so let's figure out the weight. So what is the weight in kilograms? Somebody? One of you must have a supercomputer here. There you go.
about 75.
Ooh, that's cool. Let's go.
72.7.
70 what?
72.7.
70 point, okay, so now we've got in kilograms. Now what are we going to do?
Should probably figure out how much of the drug we stuck into the person.
Well, okay.
I guess the slope that we have is in terms of that concentration, so I guess we don't really need to bother.
Take the weight to the 1/4 power.
Yeah.
What do you want to do?
Take the weight to the 1/4 power.
Yeah, okay, we want to do that too. Then,
Divide the time by the volume.
okay, then divide the time. So you want to divide time divided by 2.92. That's 8 hours divided by 0.292. And now on our plot, it's minutes. Okay? So that's equal to 8 times 60, 480. I'm just winging this, so you guys gotta.
You wrote a 6. It's an 8.
What is it? It's 60 minutes an hour?
Yes.
How about 480 minutes divided by 2.92 is equal to what?
We need to change the weight to grams.
Kilograms to grams.
Yeah.
Is it grams per kilo?
72.7.
It's grams.
See, this is in kilogram to the. So we want this to be in grams, right?
Right.
So should we go back and do this in?
Yeah. Write the 7. You just have to. Yeah.
Yeah. What do you want to multiply it then by? Huh?
And a quarter.
How much?
1,000 to the quarter.
Don't mumble.
1,000 to the quarter.
1,000 to the quarter. 10 to the 3 to the 1/4. So what does that turn out to be?
Quarter.
29.2.
How much?
29.2 total.
29.2. So this 29.2, what value is that? How are we going to use it? It's the number on the abscissa. All right, so go to that number on the abscissa And what are you going to do with it then? Okay, so someone do it. We got to get some agreement in reading this.
It's there. Could see we're just below.
What do you got?
I'm doing it.
Let's hear some numbers.
0.18.
0.18. We have a 0.18. Anyone else? Come on, take her on. Work with me, people. Work with me. 0.17. Huh? It's close enough. Now, you see, now you're getting the E20 spirit. I mean, this is only about a person's life. You know, I mean, it's... All right, so...
That's why we have medical malpractice insurance.
So 0.17, and what are the units of this thing? Micrograms per ml per what?
Milligrams per kilogram.
Per milligram per kilogram. And therefore, we're looking for what the plasma concentration is in micrograms per ml. And so what do we do to this number? Multiply it by 1. Oh, I made that too simple, didn't I? So the answer is 0.17 micrograms per ml. And so that would be the plasma concentration of methotrexate in that person 8 hours after the injection. Now, of course, it's dropping. If you go another 5 minutes or 10 minutes, it drops. But that tells you what it is. And you might be, from the standpoint of the medical practitioner, saying that after 8 hours, I need a level in the plasma of 0.3. So now what do you do? Cut their leg off so they don't have so much body weight. That'd be one way to move things around. Make the pool smaller. Cut both legs. That's like that Monty Python, just a flesh wound. Remember that? When they hacked off the arms, there's blood spurting out. What's another thing to do if I wanted to be 0.3? Increase the dose. Right? So you could go back and increase the dose until it came out to be 0.3. So that's how you work with this curve. So this isn't exact. Some people, when we get to this, think, well, was this dimensional analysis? It was. Was it even dimensional analysis on the ordinate? It has dimensions, doesn't it? So this, don't get this confused with dimensional analysis. This is scaling. And this graph actually has units. It has body weight to the 1/4 and time on the, it's strange units on the abscissa. It has units on the ordinate, but that's how it's used. So this example I use is of some historical significance because this was actually done. It was the first time that pharmacokinetics done by an engineer and a physician at the NIH brought forward an understanding as to how to relate the results in animal experiments to the results in man. And the way it used to be done is they do experiments in mice, and then they do experiments in rats, and then they do experiments in cats or dogs, and then in monkeys. And they try to estimate or extrapolate the trend to humans. Huge amount of work, and there was a high degree of uncertainty because how do you make the extrapolation other than you just start to think it must follow the same curve, when in fact all you had to do was do the experiments in one species and you could predict what would happen in man. So it was a huge breakthrough, and so I don't want you to underestimate the profoundness of this lecture when you go out. I want you to go out and I want you to look at the sun and I want you to say, I have seen it. I have seen it. And you go to the dorms tonight and inject them with something and say, I'm going to tell you what your blood concentration is in 3 hours. Inject them with milk or spaghetti or something and see what they say. All right, so we're going to make another shift in the next lecture, and that is we're going to start constructing this virtual human. And the virtual human is simply going to be a series of tanks that are interconnected that actually perform most of the functions of a human. Some of you will find this offensive and disgusting because you think you're more than a tank. You are more than one tank. You're about 4 tanks. And so just get used to it. All right? And we'll see you on, what is today? Monday. We'll see you on Wednesday.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.